Welcome everyone to MAE170, also known as Introduction to Control Systems. My name is Marco Maggia, and I will be your instructor for this quarter of summer 2021. This is a 10-week course, so we'll have more than 2 months to know more and enjoy everything about control systems. Actually, not everything, because the topic is so vast that we would need years in order to know everything about control systems, and that still wouldn't be enough. So this is just an introductory class. So we'll learn, I would say, enough in order to be able to design some controllers. So MAE170 is a natural continuation of MAE80 and MAE147. MAE80 is dynamics, and in that class you learn how to take a mechanical system, model it, find the equations of motion that describe the behavior of the system. And then in MAE147, that is vibration, we saw the behavior of a mechanical system when it is subjected to different inputs. So now the last step in this progression is to tweak the system so that the system does what we want. And that is, we want to design a controller. So once again, MAE80, MAE147, and MAE170 is the natural progression. However, don't panic if you haven't taken a vibration yet, because MAE170 and MAE147 have a lot of overlap. I mean, if you've taken it, it's better for you, good for you. You won't have to struggle as much, hopefully. But if you haven't taken it yet, don't worry, because I'll give you everything that you'll need to ace this class. Just one recommendation: follow, watch all the videos. Do not wait until the very last minute to start studying, because it's not going to work. So I'm going to be frank with you. You're most likely going to fail if you just leave all the studying at the last minute. However, if you do things diligently and you do the homework assignments, the quizzes, and watch the lectures, attend discussions, very important, every week, it's going to be much, much easier for you to not just pass the class, but pass it with a good grade, and ultimately even enjoying the topics, because we're here not just to learn, but also to enjoy. Control systems can be very fun. All right, so details about the syllabus were given in the other video that I made. So if you haven't watched it yet, please pause this video and watch the video about the syllabus and about the Canvas web page for the course. So I'm not going to give you the details about the syllabus here. However, I'll go very quickly over the tentative schedule. The course is roughly divided into 2 parts: before and after the midterm. So before the midterm, we're going to take a look at, well, going to introduce control systems, and that's what we're going to do today. We're going to see the difference and things in common between open loop and closed loop control systems. Very quickly, we're going to go over mathematical models for systems, and that is what you saw in MAE80 and then MAE147. Then in week number 1, still, we'll review the Laplace transform and the partial fraction expansion methodology. Once again, there is quite an overlap with vibration, but then I want to repeat myself. Even if you haven't taken vibration, there's no problem, because we're going to see everything once again here. In week number 2, we're gonna see the concept of transfer functions and block diagrams. We're gonna see how block diagrams are very useful when it comes to studying and play with control systems. Then the final and initial value theorems, very important theorems. And finally, errors and system types. Then we're going to focus on second order systems. Second order systems are systems that describe when we have only one degree of freedom in the system, then we're going to have a second order ordinary differential equation. So that is known as a second order system. So every degree of freedom that your system has will be associated with the second order differential equation. And second order systems are very important, although they're very simple. It's because even more complicated systems can be approximated many times, very often, using second order systems or using the analysis that we can perform on second order systems. And later we'll see the performance of feedback control systems. Then we're going to study the stability of feedback systems, and everything in this course will be focused on linear systems, same as in vibration. So if we have a nonlinear system that we start with, well, we're going to linearize the system so that we can, we're just going to deal with linear system. And there's a whole branch of control theory that deals with nonlinear system, but that is more advanced and that is for grad school. So don't worry about it. We'll just focus on linear system. But some of you might think, well, most of systems in nature and in engineering are indeed nonlinear. So why are we focusing on linear system? Well, it's because very, very often when we linearize, well, that's a very good approximation in the neighborhood of the linearization of the nonlinear system. And linear systems are much easier to study than nonlinear systems. So it's still a very, very powerful tool. And that's why we're going to focus just on linear systems. Speaking of stability of linear system, we're going to see the Routh-Hurwitz criterion to determine whether a system is stable or not. And then we're going to talk about the root locus method, which is a very powerful method. I'm going to draw. I'm going to learn how to draw. The root locus method is pretty much just a graph, a plot that tells you all the possible locations of the poles of a transfer function. You'll learn more about this later, so don't worry if you don't truly understand what I'm talking about at the moment. Then we're going to have our midterm exam, and before that, a review session. Then in part 2 of the course, well, we're going to focus more on the designing part. That is, we're going to actually design some controllers, and we're going to see two main kinds of controllers. One is the phase lead / lag compensators, and the other ones are the PID controllers. PID stands for proportional, integral, and derivative controllers. We're going to learn more about them and why they're called like that. And I actually show you that lead and lag compensators and PID controllers are pretty much the same thing. But more about that later on. So we're going to see all these controllers in both using the root locus method and later on the Bode plot method. The Bode plot is another very powerful tool that we have to study control systems when the input to the control system is a function that is harmonic. What is a harmonic function? Well, a harmonic function is a sinusoidal function. So it's just a pure sine or cosine, or a linear combination of sines and cosines. And So when the input is of that kind, then we can study the output of our system using the Bode plots, and then the Nyquist plot will introduce the Nyquist stability criterion. And finally, in week 10, we're going to take a look at some error signal analysis. In other words, how a control system reacts when we have disturbances or measurement noises. And if we change some parameters in the control system, that is the system sensitivity, how will the system behave to those unpredicted changes? Then finally, we're going to have the last review session and the final exam on Friday. All right. What's on the menu for today's lecture? Well, we have a brief introduction to control systems, then the difference between open and closed loop controls, and if we have time, a little bit about modeling and the control system design steps. But mainly what I want to focus on today is a little bit of terminology, trying to understand what we are talking about. And using the right terminology is essential because we want to learn to speak properly as well. And the other main topic for today is going to be the open versus closed loop control systems. Before describing all the terminology, which is going to be the next slide right here, I just want to give you a very basic example of what a control system is. And I'm not going to use anything fancy in any complicated system. I want you to realize that control systems are all around us, and everything we do can be taught as a control problem. For instance, let's say that you have a glass full of water on your desk, and you want to drink from that glass. So what you're going to do is you're going to your brain is going to tell you, is going to command your arm so that your arm goes and reaches the glass, grabs the glass, lifts the glass, and take it to your mouth. Well, this whole thing is a control system. And you can think about it in terms of a desired goal or a desired output. So the desired output is, let's say we would just focus on the first part of the problem, just simply reaching and grabbing the glass. So your goal is for your hand to grab properly the glass. Okay, so that's your desired goal. Now, the actual output is whether or not you are able to grab the glass like you thought you could. So what do you do? Well, using your eyes and your feelings from your hand, you guide your arm towards the glass. So you are the controller. You're using the actuator, which is your arm, in order to go and grab the glass, and you guide or control your arm using the information that you gather through your eyes and through the tactile sensation of your hand. That is, maybe your eyes are telling you that you're by the glass, and then you go and grab the glass, but you don't feel it. You don't feel it in your hand. So maybe your eyes are faulty. Your sensor is faulty. So you're using a further sensor in the tactile sensation of your hand. So you combine the information that you get from the environment until you successfully are able to grab the glass. And then part two of the problem would be just to take the glass and bring it towards your mouth in order to drink. So you see that this simple problem can be thought as a control problem. So you are the controller in this case, because you are as time goes on, commanding your arm through, you have a feedback. See, I'm using all these terminology that you can see here. Through the feedback, through the information that you get through the sensors, which in this case are your eyes and your hands, you're able to go grab the glass and then eventually take it towards your mouth. So let's now go over the actual terminology, and let's see if we can draw a parallel between the example that I gave you and a more general control system. So a system in general is just a bunch of elements or devices that are interconnected, so they're connected between one another for a desired purpose. And a control system is a system that is configured in order to reach a certain response, a certain goal. In this case, your eyes, your arm, your brain are all part of the control system. And what is the control variable? Well, that is what we want to control. For instance, that is the position of our hand. What is the controller? The controller is a device or the person that performs the control. In this example, well, it's just you, it's your brain. That is the controller. The control signal is the quantity or condition varied by the controller to affect the control variable. So in our example, that would be the input that goes from your brain to the muscles controlling your arm. And that is the control signal. So depending on the neurological signal that is sent from your brain, you can change the position of your hand. So the control signal in this case is just the electrical impulse. Then we have the process, and the process is what we want to control. So the device or the system under control. In this case, it's just your arm. The actuator is the device or the system, so the collection of devices or elements that receives the control signals and feeds it to the process. In this case, could be the nerves and the muscles that control actually your hand. And most of the times, process and actuator are fused together, and they're called the plant. So whenever you're hearing about plant, it really means the process plus the actuator. So the actuator is whatever device receives the control and then performs the control action. And then finally, we have the sensor, which is the device or the system that measures the control variables. In this case, it's your eyes and the sensation on your hand, because your eyes give you an estimate of the position of your hand. And also, it's very important that you're able to feel with your hand, and that is still a sensor. So try to get comfortable with this terminology and try to think about other examples like that. You can also think about more abstract examples like pursuing a bachelor's degree in mechanical engineering. That is still a desired output. So in order to actually get it, well, it's you are the controller. You have to do certain things. You have to convince yourself that you have to study, and instead of watching YouTube videos or playing with your phone. And those are all obstacles that you have to fight against. Anyway, pretty much you can think about anything that you perform as a control problem. And control systems and control problems are very, very often, I would say most of the times, described using these diagrams, which are called block diagrams. And each block represents a part of the control system. In this example, we have another control system example, steering a car. So your desired output is to follow the road. And well, what is your actual output is whatever the trajectory of the car is. So in this case, we have the driver, which is the controller, sends the control input to the steering mechanism, which is the actuator, and then the steering mechanism sends the signal to the car, the automobile, which is the process. Although the steering mechanism is part of the automobile, so you can think about the steering mechanism plus the automobile as what I described earlier as the plant. So driver is the controller, steering mechanism plus automobile is the plant, that is the actuator plus the process, the thing that has to be controlled, that is the car. And that gives you the actual course of travel, the actual trajectory. Can you change the course of travel? Well, if you have some sensors, so if you are able to measure the actual direction in which the car is going, and you can do that using your eyes once again, and using tactile measurements, and depending on where the car is actually is, you can change the trajectory of the car. So in this case, we're talking about a feedback loop, because we take the actual output, we measure it through a sensor, and we feed it back to the beginning, and we compare it to the desired course of travel. Are the actual and the desired course of travel the same? If so, well, don't touch anything, don't steer the car. Are you instead going in the wrong direction? Then you will have to adjust the steering wheel. So this is an example of a closed loop control system, or a feedback control system. Feedback control system and closed loop control systems are two ways of saying the same thing. So they're synonyms. If you didn't have instead a way to measure or to see, let's say that you're blind and you're wearing thick gloves, so you cannot really feel the steering wheel, well, that would be an open loop system, because you don't have any way to see or to know where you're going, or in other words, to measure the actual output. And so in that case, you would have to guess or plan ahead all the movements of your hands in order to control the steering wheel. So you don't have any measure output in that case. And if you have such system, that is called an open loop control system. And we will see that, although it sounds crazy when it comes to driving a car, open loop control systems are used and sometimes are preferred to closed loop systems. Not in this case, okay? Well, here I am just tell you that the applications of control systems can be found anywhere from physiology, economics, and pretty much all fields of engineering. Really, everything can be thought as a control system. Here I want to show you a few examples of control systems. For instance, this is a triple pendulum on a cart that we want to control and stabilize on its inverted vertical position. So naturally, this system would like to rest on its downward equilibrium. So in order to obtain this upward configuration of these three segments of the pendulum, so it's called the triple pendulum because we have three segments, well, we have to input the right controls on the cart so that the three segments are pointing upwards. This is quite of a challenging problem, and it's not as easy as it might seem. But it's nevertheless an example of a feedback control problem. Another control problem, instead, now this is an open loop control problem, is the stabilization through high frequency, high amplitude vibration of a bird or a flapping wing micro air vehicle. And this was done by Mohammed Ali Kiani in Professor Taha's laboratory. So you'll see here that, well, we'll just skip ahead a little bit. So this is a model of a hummingbird or an insect that flaps its wings. So without the wings, well, I think we can go back. Without the wings, the motion, the pitching motion of the system is unstable. So you'll see the amplitude of the oscillations just grow and grow until it just theoretically goes to infinity. Instead, if we have wings, we can flap the wings, and depending on the frequency and the amplitude of the wing flapping, we can stabilize the pitching dynamics of the system, in this case of the insect or of the hummingbird. However, if the frequency is not high enough, the pitching motion is still unstable. But if we increase the frequency, we can stabilize the pitching motion. Here in this video, the frequency has been increased. And in fact, now you'll see that when the frequency is high enough, even when we perturb the system, it will go back to its equilibrium position. So this is a case of an open loop control system in which we are not sensing the position or the pitching angle of the bird, but we are controlling simply through a high frequency, high amplitude input in terms of the flapping of the wings. So that is an example of so-called vibrational open loop control. In this other video, we can see a kestrel that is hovering, and you'll see how it moves its tail and wings in order to hover. So it's a different dynamics than the hummingbird or the insects, but you'll see how it can stabilize its head perfectly by doing little adjustments. In this case, this is a feedback control system because the bird senses its actual position and changes the position of its tail and the wings, which are the controllers, in order to stabilize its head, that is the desired output. Finally, we have an example of a self-balancing stick. So obviously, if you have a stick, if you just let it go, the stick would fall. But we can put these two actuators as these reaction wheels. And if we spin these reaction wheels with the proper velocity and in the proper direction, we can overcome the natural tendency of the stick of falling, and we can balance the stick in this unnaturally unstable position. And you'll see that even when we perturb the stick, let's see, perturbation should be, or here we attach a weight, then the reaction will spin in a way that the overall desired vertical position of the stick is maintained. And let's see if we have. Here, the perturbation, sorry. Well, if we remove or add a weight, this still counts as a perturbation, and this can handle it. Of course, if the perturbation is too large, the system might not handle it. Anyway, this is once again an example of a closed loop control system. You see here, you can find many other examples on YouTube, or if you just think about it. All right, so here you have the links to those 4 videos that I showed you. All right, so let's go back to just a visualization in terms of block diagrams of the process. So the process is what we want to control. So whatever, we can visualize the process as a black box, which is given an input, and then we'll spit out an output. And hopefully the output is what we want. And as I anticipated, there are 2 main types of control system. The open loop control system, in which we have no feedback of the actual output. So we have no idea, we cannot measure the output. So we hope that the output is what we want. And instead, the closed loop control systems are much more reliable because we can actually measure the output and adjust through the controller, actuator, and process. So if the process per se does not behave like we want, well, we can add the couple controller and actuator. So using the controller would just generate the control law, which will be passed to the actuator, and the actuator will actually modify the behavior of the process. But once again here, this can be done on an open loop or a closed loop control basis. In this case, if we cannot measure the actual output, as I said, we're talking about open loop control systems. You can think about it as an example, let's say a washing machine. So you put your clothes in and you set up the time, the temperature, and everything. So that is like your control law. And your desired output is that the clothes come out clean, okay, without stains, and they smell good. However, there's not really a way to sense that, at least in, maybe there are some very fancy washing machines that can tell how clean the clothes are. But let's say, you know, old style washing machine, you cannot really tell if the clothes are clean. So you have to hope that at the end of the cycle, the clothes are clean. You cannot measure the output in terms of cleanliness of the clothes. So this is an example of an open loop control system. You cannot measure the cleanliness of the clothes, that is the actual output, and only at the end of the process of washing the clothes, you can you can verify whether the clothes are actually clean or not. So open loop control systems are used when the output cannot be measured, or is very, very difficult to measure, or in order to measure the output, you would have to create a system that is very, very complicated or very costly. So it's not worth it. So sometimes you just use open loop control systems. And another example of open loop control system, or when open loop control systems are used, is when the system, the process is known very, very well. You know that there are not going to be disturbances and or variations. Let's say the environment is very controlled. You expect it to behave exactly like you've predicted. You've modeled the system very, very well. So you can just use an open loop control system tactic. Usually, all control systems that operates on a time basis are open loop. Another example, microwave. Let's say that you want your milk warmed up and you put 1 minute, and but you're not really measuring the temperature of the milk while it's heating up. So you hope that at the end of the minute, your milk is warmed up. You know, usually, at least I warmed up 1 minute, because that's the temperature of the milk that I like. So I know that for that quantity of milk, for that mug that I'm using, for the microwave that I'm using, 1 minute is the right time. So I know there's not going to be disturbances or errors, and therefore I'm using an open loop control system in order to warm up my milk. All right, well, drying clothes can be thought also as a open loop control system, which we have the timer, heating elements, and the clothes are the process, that is the thing that you want to dry. What are the pros of open loop control systems? Well, they are of simple construction, or simpler construction, and it's easier to maintain them. So they are usually less expensive with respect to a corresponding closed loop system. And they're convenient when the output is hard to measure, or it is very difficult or economically not feasible to measure the output. However, the cons of open loop control system is that if the system is badly modeled, or if you have disturbances, you're gonna get poor performance. And also, you want to make sure that you know your control system very well, so you need to calibrate it very, very frequently. You the system itself cannot take care of variations that will happen in the system. On the other hand, we have closed loop control system. Those are, I would say, ideal most of the times, because you don't need to model your system perfectly, because the feedback loop will take care of disturbances or errors in modeling. Of course, you still want to start with a good model for your system. However, the closed loop control systems are a little bit more complicated, because they require a sensor that reads the actual output. And this actual output has to be compared to the desired output, so that the error, that is the difference between the desired output and the actual output, is driven to 0. I already gave you a few examples of a closed loop control system. Another one could be the temperature regulation in your body. If it is too hot, then your body starts sweating, so that your convection coefficient increases, so that you can exchange or lose more heat towards the environment, and therefore your temperature goes down. So it's another example of feedback control system. And we saw here are another couple of examples: steering of a car, we already saw, or the cruise control. I'll leave it to you to analyze, but I think you've gotten the gist by now. What are the pros then of the closed loop control systems? Well, they're relatively insensitive to external disturbances and internal variation in the system parameters. They can handle measurement noise. They are more versatile than open loop systems. They do not need constant calibration or perfect modeling of the system, and can even handle more variables to control at the same time. And here, multi-input, multi-output is also known as MIMO, or SISO is single input, single output. In this course, we'll just focus on single input, single output control systems. However, we have also obviously cons connected to closed loop control systems. Well, we have a problem in terms of stability. That is, if we overcorrect using a feedback loop, we can make the system unstable. We'll see that. And generally, closed loop control systems are more complex and elaborated than the corresponding open loop ones. And they might be quite difficult to design when the output is hard to measure. Here, there's another example, the turntable, open loop or closed loop control. I'll leave it to you to take a look. And one last thing that I want to see today is, well, how can we design? Just now, we're not going to go in depth, mathematically speaking, in terms of design. We will see that later on, but just conceptually, how can you design a control system? Well, step number one, you have to understand what you want to control. So you have to come up with your problem, and you want to come up with a good model that describes your system that you want to control. And so you want to know exactly how your system behaves, or a prediction of how your system behaves given different inputs. And so, in other words, you want to write down some equations, that is, ordinary differential equations, the equations of motion that describe the dynamical behavior of a system. And that's what we saw, or you saw, in vibrations and in dynamics, but we're gonna take a look at that. And then once you know your system, well, you want to establish some requirements. So what do you want your system to perform? Then what you're gonna do, you transform these requirements from physical requirements. Let's say I want to grab the glass of water as fast as possible, let's say in less than 0.1 second. Well, I have to translate the requirements into mathematical constraints, and then using the dynamics of your system plus the constraints that are the requirements that you want to achieve, then you can design the controller and design the control algorithm. All right, so as I said, step number one is to be able to model your system. In other words, you want to be able to predict the dynamic behavior of your system. And if you have, once you've modeled the system, if you end up with the nonlinear model, well, you want to linearize it, at least as far as this course is concerned. We're going to deal only with linear systems. For instance, we have an RC circuit. If we have a resistor and a capacitor, well, given a certain input in terms of difference in voltage, what is going to be the difference in voltage at the output? Well, in order to do that, here we don't really have a controller yet. We just want to model the system. We want to know how the system behaves before we design the controller. So we have to come up with an equation that describes the output and correlates the output with the input. So in this case, we have, using the capacitor current, I equals C times dV over dt. And again, we're not going to really cover how to get to the equations. We will just assume that we're given the equations, or you know how to get them. But you can relate the input and the output. So in this case, it's just for the RC circuit. For a car suspension, for instance, we can model it, as my cat is pointing out, with the mass attached with the spring and a damper. So in this case, our input is an external force, and the output is the position of the mass. So the model is just described by a second order equation. As I told you in the beginning, every mechanical system, but I think it's worth to repeat it, every mechanical system is described by a second order ordinary differential equation per degree of freedom. So in this case, we have a mechanical system, yes, mass. How many degrees of freedom do we have? Just one, because the mass can only oscillate vertically. And so mathematically speaking, that will be translated into a one second order ordinary differential equation. Second order because we have a variable that is the position of the mass, x output, that appears with its second derivative at most. All right, I'll stop here for today. We've covered enough. So once again, the main key points is control systems, terminology, realize that control systems are everywhere, difference between open loop and closed loop control systems. And then before actually designing the control systems, we need to be able to model the system that we want to control very well. And that is done through modeling and eventually getting the equations, ordinary differential equations that describe the motion of your system. All right, this is all for today, and I'll see you virtually next time. Take care.